All right, so today we're not actually going to be using Desmos. We're going to kind of veer a little bit away from the book here to condense things a bit and sort of focus things a little bit. So our goal for today is going to be to graph polynomial functions just using the factored form of a polynomial. So let's talk about how we're going to do that. Before we can jump into just the graphing part of it, let's actually make sure that we're all using the same terms. So when we look at a graph, we'll be able to tell a lot about what the equation might look like just by glancing at the graph itself. So here's what I notice in graph 1. I notice that both ends of this graph point in the same direction. Okay, so both ends point in the same direction. Whereas in the second graph, the ends point in different directions. Now, what that means for us is the equation is going to have something going on that will be easy for us to identify. In the graph on the left, what we notice is that since both ends point in the same direction, that tells us that our highest power is an even number. Whereas both ends pointing in, or the ends pointing in different direction, tell us that the highest power is an odd number. Okay, so in the first graph, our highest power, this might be a power of 4. We'll be able to tell a little bit more a little bit later. In the graph on the right, our highest power might be 7. Okay, so we're talking about the highest power is based on the direction, how they're pointing. I noticed that, so that would be number 1. Number 2, what I notice is that in the graph on the right, or on the left, sorry, the right side of the graph points up versus the graph on the right side of the graph is pointing down. So on the first graph, the right side points up. Here, our right side points down. Now what that tells us, let me just move this up a little bit so I can write a little bit better, is that the overall graph will be positive if the right side points up and negative if the right side points down. So our graph is going to have a negative, sorry, this one has a positive. We're going to call it a value, or you can think of it as stretch factor. Whereas here, we'll have a negative a value, or you can think of it again as your stretch factor. Okay, one or two more things that we can look at here. The number of times that our graph intersects the x-axis is going to help us figure out how many solutions there are. And we talked a little bit about this in prior lessons. So when we look at this, I noticed that the first graph intersects at 1, 2, 3 places. So, you know, logically we would say, oh, okay, well, it has 3 solutions. But there's something special about the way 2 of them intersect the axis. So I want to talk about really the 3 different ways you might see your graph interact with the x-axis. This first way, our graph, if we look at it, just passes through the x-axis. The second one, we can see that it bounces off of the x-axis. And then the third one, it passes through, but it also kind of does so in a much kind of more gradual manner than the original one. We can see how it sort of like gets slower and it's increasing, and then it starts to pick up again. We call that sliding through the x-axis. Okay, so we have these three different ways that the graph interacts with the x-axis. This affects what we call our multiplicity of a function. Okay, so the multiplicity says how many times will that root actually be used. So let's zoom in a little bit. If I just zoom in on that first intersection point and we just focus on what we can see of the graph, this looks a lot like a linear function. So its multiplicity will be 1. If we zoom in on the second intersection point, we can almost see how this looks a lot like a quadratic. Because a quadratic has a power of 2, this is going to have a multiplicity of 2. And sometimes it could be 4 or 6 or 8, but it has some kind of even multiplicity. That means that this root is repeated an even number of times. So maybe it's repeated twice, maybe it's repeated 4 times, but it has to be repeated an even number of times. And then finally, if I zoom in on the last intersection, I can see how, this graph almost looks a little bit like a cubic graph, right? It's no longer linear in fashion. It looks a lot like a cubic graph. So what that tells us is that this will have a multiplicity of 3, meaning that this root will be repeated in our equation 3 times or some multiple of 3. So it could be repeated 3 times or 6 times or 9 times, depending on the equation itself. Now let's zoom back out. So let's summarize what we just found. We said if it has a multiplicity of 1, think linear. Okay, so let me move this up again here. So a multiplicity of 1 that means our root, and this will go for both graphs, is only used once in the equation. And it's going to look linear when you zoom in. Okay. Then we have the possibility of having a multiplicity of 2, and I'm going to put here or 4, 6, 8, ... meaning any even number, okay? So our root is used an even number of times in the equation. It looks quadratic when you zoom in. And then finally, we could have a multiplicity of 3, and again I'll put or 5, 7, 9. And I may have said that wrong earlier, I think I did. Has to be an odd number, all right? So the root is used an odd number of times in the equation. Okay, it's going to look, it looks cubic when you zoom in. So let's go back up to that graph on the right, and let's just decipher what's happening with the roots, okay? So at this one, that one's pretty easy to see. It looks pretty linear. So this would have a multiplicity of 1. Here, it's passing through. Now, that's not quite as linear maybe initially, but if we were to zoom in and just look really close to 1, it does have kind of a linear look to it. Again, this would be a multiplicity of 1. Now, this one's a little tricky. It doesn't bounce. It slides through that root. And again, if you zoom in, you'll see it slides through. So this is going to have a multiplicity of you know, either 3, 5, 7, dot, dot, dot. We don't really know. It's going to be an odd number, though. All right, so let's see if we can use that to start graphing our functions. Now, what you're going to see as we move on from one example, from the first example to the next examples, we are always going to use, or not always, but for this lesson, we're going to use the factored form of the equation. So the first thing I want to do here is factor this equation. I should be able to factor this relatively quickly to 2x minus 3 times x plus 4. Now what I want to do is identify a few important details about this graph. The first thing I want to do is identify what we call the degree. Now the degree is just the highest power. And what this is going to allow me to do is figure out whether it's even or odd. So in this one, my degree is 2. That is even. Okay, I'm going to come back to that in just a second. Second thing I'm going to look at is my a value, or stretch. Okay, so that's a positive number. I can see that either here, or just whatever's here, right? If that's a positive number, that's all we're really concerned about. So the stretch factor is positive. Now what that means is this. If the stretch factor is positive, based on what we said on the other screen here, we know that the right side will point up, points towards positive infinity. So on the right side of the graph, our graph will point up. It's going towards positive infinity. Our degree is 2, which is an even number. That means that both sides of the graph point in the same direction. So that means that if the right side points up, the left side will also point up. So what we know, we don't know what's happening in the middle of our graph, but we know that on the right side and the left side, both ends will point up. The next thing I want to do is identify all roots with their multiplicity. I'm just going to write multiplicity as abbreviated there. So I'm going to take each of these, set them equal to 0. Sorry about that. And I get x equals 3/2 and x equals -4. So I have a root at 3/2, 0, and that has a multiplicity of 1 because it's not repeated. I have a root at -4, 0, which also has a multiplicity of 1 because it's not repeated. Now, using all of that information, we can get a sketch of the graph. So the only thing that's left to do is to actually just sketch the graph. Now, here's the thing about this whole process that's important to understand. We are just sketching these graphs, and I'll show you why that's important here in just a second. So the first thing I'm going to do is I'm going to make a note to self. Both sides of the graph point up. So on my graph, I'm just going to do this. I'm going to say this side points up, this side points up, just so I remember, hey, that's going to be pointing up. Second thing I'm going to do is put my roots on here. So 3/2, 0, that's 1.5, 0, that's like right here. And then -4, 0 would be right about there. Now, from there, I know that these are multiplicity of 1, which means they pass through the graph, kind of like a linear function would if we were to zoom in on that little portion of the graph. So what I know is I'm going to start up, I'm going to pass through this point, I'm going to come down below it somewhere, I don't know where, and then pass through again, and I end up with something that looks like this. Now, I could make this more quadratic since I do know it's a quadratic. Oops, let me do this a little bit nicer here. But the key is the right side of the left side of my graph are pointing up. I've just passed through each of these roots. As far as how deep the graph will go, or where the lowest point is, you know, I could maybe do this instead, right? I might draw the graph and make it look like this. We are doing a sketch of this graph. So I'm not going to be so concerned about where the vertex is. Okay? I'm just concerned with getting a sketch of this graph. So any one of those that I have drawn on there would be an acceptable sketch. Okay, let's try another one. So this time I've already factored it for you. We've got a polynomial, and we're going to talk through the same kind of talking points that we talked through last time. The first thing I'm going to do is I'm going to consider whether or not my function is a positive or a negative stretch value. So is A, or my stretch factor, positive or negative? And that's going to determine what happens on the right side of my graph. So if I look at this function, my A value, if there's a negative sign out here, that means it's a negative A value. If there's nothing here, it's a positive A value. So my A value is positive. Now what that means is that the right side of the graph points up. Okay, second piece of information that I have is what the degree of this polynomial is. In other words, what's the highest power? Now to figure this out, I have to consider what would happen if I were to multiply this whole function out. So if I were to multiply this guy out, I would get x squared as my highest power. Now there would be some stuff after that. I'm not concerned about the stuff after it. And then I have this x term here that I would multiply it by. That's going to give me a highest power of x cubed. Now there's going to be some other stuff after it. Don't care what that stuff is. I'm only focused on what's the highest power. So in this case, my highest power is 3. Now that is an odd number. So what that tells me is that the ends of the graph point in different directions. So I know if the right side has to point up because of what we found in the previous thing, then the left side has to point down. Again, I don't know what's happening in the middle of the graph, don't care. And the third thing I do is I find all of my roots or my x-intercepts. Okay, and I do that by taking each factor and setting it equal to 0. Now, I could rewrite my equation as x minus 1 times x minus 1 times x plus 5. And that helps me see that this 2 actually means that root is repeated twice. So that tells me that this root has a multiplicity of 2. All right, so I'm going to do that. So I'm going to have x minus 1 set equal to 0. Sorry about that. I get x equals 1. And then and that takes care of both of these. Then I'm going to do my x plus 5 set equal to 0. And I get x equals negative 5. So what I find are my two roots are the point 1, 0 and negative 5, 0. Now, this one has a multiplicity of 1. This one, however, has a multiplicity of 2. So we're going to see our graph bounce or look like a quadratic at the point 1, 0. So let's graph it. So once again, based on what we've already figured out, I know that the right side points up, left side points down. Okay, just make myself a little note there. Then I'm going to go ahead and put my roots on there. Now, 1, 0, I know there's going to be a bounce there. Negative 5, 0, it's going to pass through. So maybe you put a little note to yourself here. If you want to put bounce as a little note, you can. You don't have to, but you can. Now I need to sketch the graph. So I know it starts on the left side of the graph from below the x-axis. So I'm going to start drawing my graph. I know that at negative 5, it's a multiplicity of 1, so it's just going to pass through. So it passes through. Now I know that it has to get back to 1, 0. What I don't know is how high it's going to be. So we're just going to guesstimate. We're just going to take a guess. We're going to say, okay, it has to keep going, but it has to come back down to this 1. And at this point, it's going to create a little parabola there. So it bounces off that root. And then I know it's going to finish off by going up. Now, how you finish that, could look different. And the thing that's important is just that we have this general shape. So what I'm looking for is, are the ends of your graph pointing in the right direction? Are any of your multiplicities being shown as a bounce or a pass through or a slide? And that's basically it. Those are the things that have to be met. The other thing you have to watch is don't create any extra x-intercepts. Okay, so don't make it go through the x-axis again. All right, let's do another one. All right, so our process is first to decide whether a is positive or negative, find the degree, and then find the roots. So now when we look at this function, I see that we have this negative number out here. This is like saying negative 1 times x. So I could write that, you know, instead of just negative here, I could say that's -1 times x. So I have an a value that's negative. Now what that tells me is that the right side of the graph is going to point down. All right. Now, next I find the degree. Now we have to think about this sort of generically. We have an x here. We're going to multiply that by an x cubed here. And then we're going to multiply that by another x. Now there's a whole bunch of stuff in there as well, but we don't care about what all of that other stuff is. We only care what the highest power is. So we end up with something that looks like x to the 5th. So our degree is 5, which is odd, which means the ends point in different directions. So we already decided that the right side has to point down, which means the left side has to point up. We don't know what happens in the middle. We're going to figure that out in a second. Now let's take each of our roots and find them. So the one, I'm going to rewrite this one more time here just so it's a little bit easier to look at. Now you could write that as x plus 3 times x plus 3 times x plus 3 if you want. You don't have to. But let's find our roots. So don't forget about this one. That is a root. Set it equal to 0. X equals 0. That's going to give you one of your solutions. Set x plus 3 equal to 0. We get x equals -3. And then we have x minus 2 equals 0 as our only other option, because each of these is going to give you the same solution. So when I talk about my roots, I'm going to have from here the point 0, 0. Now it has a multiplicity of 1 because I only see it one time in my equation, so multiplicity of 1. Then I have the root -3, 0. Now this one has a multiplicity of 3. So when I graph this, this is going to be one that's got kind of a slide. So we talked about how it'll look sort of like a cubic function at the point -3, 0. And then finally I have the point 2, 0 as a root that has, again, a multiplicity of 1. So let's try to graph this. Okay, so let's put on here what we know. We know that the right side of the graph points up. I'm sorry, the right side of the graph points down because it's a negative function. And we know that the left side is going to point up because it's an odd power. Then we put our roots on here. 0, 0, -3, 0. We know that's going to have a funny kind of behavior there. We'll talk about that. And then 2, 0. So when we start connecting our points, we know we start above the x-axis because the right side of our graph has to point up. So I'm going to start above the x-axis, and I'm going to go through the point -3, 0, but I have to sort of create a pass through there that sort of looks like a really little cubic function there. So when I draw it, I'm thinking, I want to make like a little cubic function here. I'm sorry. Okay, so something like that. It's not perfect, and that's okay. I'm having a hard time drawing this on my iPad, but I know that this side's going to point up because that's the end of my graph. And then at some point, I've got to turn around and come back through 0, 0. So let's just turn around and go through 0, 0. 0, 0 is just a pass through. There's no bounce there. There's no little slide. We just go right through it. Okay, and then we go through it and we say, okay, well, we got to turn around now and go back through 2, 0 because that's another one of my roots. So I'm going to turn around here. I don't know where I turn around. Maybe it's up higher, maybe it's down lower. Who knows? Who cares? We're just getting a sketch. And then I pass through there. And then I know that's it. I don't have any other intercepts. I can't go through the x-axis again because my graph doesn't allow for any other x-intercepts. And I know that the right side needs to point down. So that's what our graph would look like. Remember, this is a sketch. If you were to put this into Desmos or a graphing calculator or other graphing utility, you're going to see a more detailed graph. I don't care what it is. We're just doing a sketch here. Okay, last one, very similar to the previous example. Let's start with our a value. Is it positive or negative? Once again, it is negative because of that negative there. So this has a negative behavior. I guess I don't need to put negative in quotation marks. Negative behavior, which means the right side of our graph points down. Second part we figure out is what is the degree of our function. What would be the highest power? Okay, well, we've got an x here that we would multiply by an x cubed here that we would multiply by an x squared here. So when I multiply those all together, I'm going to get x to the 6th. That gives me an even degree, which means both ends are going to point in the same direction. So both ends are going to point down. Again, I don't know what's happening in the middle. I will figure that out. And then finally, let's find all of our roots. Just like in the previous problem, don't forget about that x out in front. If you continue to want to write these to help you remember what the multiplicity is, you are free to do so. I'm going to run out of room there. So I'm going to set each root equal to 0. X equals 0. That just gives me my first root of 0, 0 with a multiplicity of 1. Then I can take this x plus 3 and set it equal to 0. That gives me x equals negative 3. Now that's going to be the same for all three of those roots. So I get the root negative 3, 0, but this time it's a multiplicity of 3. That translates to a slide on our graph. And then finally, I can take x minus 2 and set it equal to 0. I get x equals 2, but that's the same root again. So when I look at my photo, when I look at my picture, I'm going to have the root 2, 0 with a multiplicity of 2. That's a bounce. So your slide is going to look like a little x cubed graph, while your bounce is going to look like a quadratic at that particular root. All right, let's graph it. Okay, so I wanted to kind of keep at least the root showing. We said this was a negative graph, which means the right side points down, but it has an even power, it has an even degree, so that means the ends are going to point in the same direction. So since the right side points down, then the left side will point down as well. Let's graph our three roots, 0, 0, negative 3, 0, and 2, 0, and we need to pay attention to any multiplicities so we make sure we get the behavior correct. Now this time we're coming up from under the x-axis to begin our graph. So let's go ahead and graph this now. I'm going to start below the x-axis since the left side of my graph is pointing towards negative infinity. And I know that I'm going to do a slide through negative 3, 0. So I'll just kind of slide through there. Now I come up through there, and at 0, 0, I've got to have a pass through. So at some point I have to turn around. So maybe I turn around right here. And I say, all right, well, I got to go through 0, 0 as a pass-through. And then at some point, I have to turn around again. But this time, because we have a multiplicity of 2 on this root, we're going to just bounce off of it like it's a little parabola right here. And then we continue to move down because we know that our graph has to point down on the right side. So this is just, again, a quick sketch of this graph just by knowing some very basic information.